In the last discussion, we had started in the last lecture, we had started our discussion on pressure driven flows. Pressure is a mechanism for momentum transport which does not have an analogy in mass and heat transport. In mass and heat transport, the only mechanism of transport is either convection or diffusion. Whereas in momentum transport, there is diffusive transport of course. The shear stress is equal to the viscosity times the velocity gradient, Newton's law of viscosity. However, there is also an additional mechanism which is a pressure difference. So, a pressure difference across the ends of a pipe, for example, will result in a flow. However, pressure is defined even in the absence of flow. Even if you have a static column of fluid as shown here, there is a pressure acting due to that fluid on the base and on the sides. Even within the fluid, if you take a small differential volume, there is pressure acting on the sides of that volume. For a differential volume, the pressure is always compressive. It always acts along the outward unit normal. Recall that we had defined, for example, the shear stress as tau xz. Tau xz is the force per unit area on the in the x direction acting at a surface whose outward unit normal is in the z direction. Similarly, I can define, for example, tau xx is equal to force per area in x direction acting at surface with outward unit normal in x direction. And similarly tau yy and so on, those are not related by Newton's law. So, we will see that when we do momentum transfer, those components are not related by Newton's law. However, this is the definition of the stress, force per unit area in the x direction acting at a surface whose outward unit normal is in the z direction. The pressure acts along the inward unit normal. So, tau xx is equal to minus p for the surfaces whose outward unit normal is in the x direction. Similarly, for the surfaces whose outward unit normal is in the y direction, tau yy is equal to minus p. And tau zz is equal to minus p. This is for a static fluid in the absence of any flow. All the components, the normal components of the stress are all proportional to, are all equal to minus of the pressure in the absence of flow. In the presence of flow, of course, this relation does not hold, but in the absence of flow for a static system, these pressure is equal to minus tau xx equals minus tau yy is equal to minus tau zz. I had also drawn a distinction between thermodynamic and dynamical pressure. The thermodynamic pressure is an absolute pressure. It is always positive. For gases, it is given by ideal gas law, P is equal to nRT. T is the absolute temperature, so it is always positive, and N is the number density, it has to be positive. The dynamical pressure, on the other hand, is what drives flow. So, for example, in the atmosphere, for example, changes in pressure over at different locations will drive flow in the atmosphere, for example. Those dynamical pressures are pressure differences. You define it relative to a reference pressure, usually the atmospheric pressure. So, as far as flow is concerned, what matters are pressure differences and not the absolute pressure itself. If the fluid is incompressible, that is, there are no variations in density, then you can add a constant pressure everywhere in the flow domain, and the fluid velocity field will not change, okay. Because as far as the fluid velocity is concerned, what matters is the difference in pressure, okay. So, as an example, for a laminar flow in a pipe, right, what matters for the velocity is the difference in pressure between the ends. I can add a constant pressure on both sides and the velocity in the pipe will not change, okay. So, there is a difference between the dynamical pressure and the thermodynamic pressure. In this discussion, we will deal exclusively with the dynamical pressure, okay. So, the pressure could be positive or negative. What matters is the pressure difference or the pressure variation with location. Okay. So, we had done a balance, a shell balance across a differential volume in a cylindrical coordinate system. Okay. This differential volume has two cylindrical surfaces at r and r plus delta r, and two flat surfaces in the form of annular discs at x and x plus delta x. And the balance condition was that the rate of change of momentum is equal to rate of momentum in minus the rate of momentum out plus the sum of forces. It is important to note the direction of the forces in this case. Okay. So, at the surface at r plus delta r, okay, the cylindrical surface at r plus delta r, okay, tau x r is the force per unit area in the x direction acting as a surface whose outward unit normal is in the r direction. Okay. So, at this surface at r plus delta r, the outward unit normal is in the r direction. Okay. Therefore, the force is tau x r times the surface area, 2 pi r plus delta r times delta x. Okay. The perimeter 2 pi r plus delta r for this outer surface times delta x times tau x r at r plus delta r is the force acting on the outer surface. On the inner surface, the outward unit normal to the volume is acting in the minus r direction, okay, on this inner surface. Okay. That means that the force per unit area is minus tau x r, because if you reverse the direction of the unit normal, the direction of the stress is reversed, or the direction of the force is reversed. Okay. So, therefore, the force on the inner unit normal is equal to minus tau x r at r into 2 pi r delta r. Okay. So, those were the forces on the cylindrical surfaces. There are also forces on the flat annular surfaces. Okay. For the surface at the location x, okay, that is between these two circles, okay, for the force at the location x between these two circles, right, the pressure acts along the inward unit normal. So, in this particular case, the pressure is in the plus x direction, and the force is pressure at the location x times the surface area, okay. That is P times 2 pi r delta r at the location x times 2 pi r delta r. At the surface at x plus delta x, okay, that is this particular surface, okay, between this circle and this inner circle, okay, at the location at x plus delta x, pressure acts inward, that is in the minus x direction. Okay. So, therefore, the force is minus P at x plus delta x times 2 pi r delta r. Okay. We also had momentum in and momentum out. Okay. Momentum in is the momentum density times the velocity times the area, okay, because the momentum flux is the momentum density times the perpendicular velocity. Okay. The momentum flux is the momentum density times the perpendicular velocity. That multiplied by the surface area is the momentum coming in per unit time. Okay. That multiplied by the surface area is the momentum coming in per unit time. Okay. Rho Vx is the momentum density, Vx is the perpendicular velocity into 2 pi r delta r is the surface area. Momentum coming in, rate of momentum in at x. And similarly, we had a rate of momentum out at x plus delta x. Okay. And when we did the balance, we had said that for a fully developed flow, if the density is a constant, this rate of momentum in and the rate of momentum out have to be exactly the same, okay, if the density is a constant. So, I will briefly go through the mass conservation equation to explain why that is so. Okay. I will go through the mass conservation equation to explain why that is so. Okay. So, once again our cylindrical differential volume between the locations r and r plus delta r and x plus delta x. Okay. Okay. And we write the mass conservation equation for this. Okay. Change in mass in time delta t, okay, is equal to mass in minus mass out plus the production. Okay. Of mass, okay, in this time delta t. We will neglect the production for the time being. So far we have been writing the equations for the concentration. This is for the total mass, the total density, okay, of the fluid, okay, the sum of all the concentrations. Okay, that's what we are writing this equation for. Okay. And then the mass in and the mass out is due to the fluid velocity. Okay. The mass in and the mass out is due to the fluid velocity. Fluid velocity is only along the axis. Okay. The fluid velocity is only along the axis in the x direction. Okay. It is only in the x direction. There is no velocity perpendicular to the cylindrical surfaces. Okay. So, this is a unidirectional flow. The velocity is only in the x direction. Okay. So, change in mass in time delta t is going to be equal to the mass at time t plus delta t minus the mass at time t. Okay. That is going to be equal to rho at, okay, r x t plus delta t, okay, or is equal to the density at r x t plus delta t minus the density at r x t, okay, into the volume. Okay. Volume 2 pi r delta x. Okay. So, we had already seen that earlier. Okay. Okay. Volume is 2 pi r delta x. Okay. So, therefore, I have here okay, that is the change in mass. Okay. What is the mass in? Okay. Is going to be equal to the mass density times the perpendicular velocity times the surface area. In this case, mass is coming in at the surface at x. Okay. Mass is coming in at the surface at x for this differential volume. Okay. So, this is going to be equal to rho the mass density times the perpendicular velocity V x, okay, at the location x into the surface area. The surface area is 2 pi r delta r. Okay. That is this surface area, the surface area of the surface at the location x. The surface area is the same at the location x and x plus delta x. Okay. So, this is the surface area at the location x, okay, which is the same as the location x plus delta x. Okay. So, therefore, the mass out I am sorry, you have to multiply by delta T as well, okay, is equal to the mass flux times the surface area times delta T. Mass flux is mass density times the perpendicular velocity to the surface. Okay. Similarly, mass out is equal to rho V x at x plus delta x 2 pi r delta t. Okay. So, if I go through and determine the conservation condition here, okay, change in mass, okay, rho at r x t plus delta t minus rho at r x t, okay, into the volume 2 pi r delta x is equal to mass in minus mass out, which is rho V x at x minus rho V x at x plus delta x, okay, 2 pi r delta t. Okay. So, this is the conservation condition for a unidirectional flow where there is no flow out of the cylindrical surfaces. Okay. There is no velocity in the radial direction, the velocity is along the axis of the pipe. Okay. So, in that case you get this conservation equation. Divide by volume and divide by time, okay, 2 pi r delta x delta t. Divide by volume, divide by time, and you will get rho at r x t plus delta t minus rho at r x t by delta t, okay, is equal to rho V x at x minus rho V x at x plus delta x divided by delta x. Okay. And take the limit delta x going to 0, delta t going to 0, equation becomes partial rho by partial t is equal to minus partial of rho V x by partial x. Okay. And incompressible, partial rho by partial t is equal to 0 and partial rho by partial x is equal to 0. Okay. So, both the density is a constant, and you can easily verify that this will reduce to 0 is equal to minus partial V x by partial x. Okay. So, if partial V x by partial x, okay, so the divide throughout by rho and use the condition that the density is a constant. So, flow is incompressible. Okay. So, therefore, for an incompressible flow unidirectional, the velocity has to be independent of x. Okay. For a unidirectional incompressible flow, it has to be independent of x. It does not have to be independent of time. Okay. The velocity does not have to be independent of t. Okay. So, therefore, because of that we had neglected, okay, these two terms, okay, rho V x square at x minus rho V x square at x plus delta x for an incompressible flow. Okay. Because density is a constant and V x is independent of x. It is not independent of time, however, therefore, you do have this term on the left side, okay, for an incompressible flow. A flow is incompressible provided the velocity, flow velocity is much smaller than the speed of sound. Okay. So, typically in air at room temperature and atmospheric pressure, the speed of sound is of the order of 330 meters per second. So long as the flow velocity is much smaller than that, approximately 330 meters per second, the flow can be considered incompressible. Okay. In liquids, the speed of sound is much higher. So, in water, for example, the speed of sound is about 1500 meters per second. Okay. So, there is a larger range of flow velocities over which the flow can be considered incompressible in liquids. Okay. So long as that is the case, the conservation equation is rho partial Vx by partial t is equal to partial by partial x, partial by partial of minus partial p by partial x. Okay. And if the viscosity is a constant, okay, so I can divide throughout by the density firstly. For an incompressible flow, I can just divide throughout by the density and get partial Vx by partial t is equal to 1 by r d by dr of r nu partial Vx by partial r. Density is a constant, so I can take it within the derivative. Okay. Okay. And if in addition the viscosity is also a constant, in addition the viscosity is also a constant, then the equation becomes partial Vx by partial t is equal to nu by r partial by partial r of r partial Vx by partial r minus 1 by rho partial p by partial x. That is the momentum conservation equation for the flow in a pipe. Note here that pressure is a function of x. Okay. Pressure cannot be a function of r in this case, because there is no flow in the r direction. Okay. If I were to write a momentum balance similarly for the radial velocity, okay, if I were to write a momentum balance similarly for the radial velocity for this cylindrical volume, okay, for this cylindrical volume, if I were to write a balance equation similarly for the radial velocity, okay, where x is in this direction, r is in this direction. Okay. So, once again I will have to take the radial momentum in, the radial momentum out, and the difference in pressure along the two cylindrical surfaces in the radial direction. Okay. So, in the r momentum balance equation, the pressure acting in the radial direction is acting on the cylindrical surfaces. Okay. The pressure acting in the radial direction is acting on the cylindrical surfaces. Okay. So, I will have to write an equation for the pressure difference at r and r plus delta r plus the stress, okay, the stress in the radial direction and the momentum in, momentum out in the radial direction. In those equations for the stress, okay, the radial velocity is equal to 0. Okay. So, the shear stress is equal to 0 because there is no radial velocity, okay, in the r direction. Okay. So, if I were to write this equation for the radial direction, the only contributions I would get is due to the pressure difference. Okay. And the pressure difference, that contribution would basically tell me that partial p by partial r is equal to 0, or the pressure has to be a constant in the radial direction. Okay. So, that is the solution in the radial direction, there is no pressure variation in the radial direction. Okay. So, the pressure for a laminar flow is a constant across the radius, okay, because there is no velocity in the radial direction. What about the pressure gradient? Okay. This term here is called the pressure gradient. Okay. How does that pressure gradient vary in the x direction? We know the difference between the ends of the pipe, of course, because that is the applied pressure. But how does that pressure decrease between the two ends of the pipe? Okay. So, in other words, the question I am asking is, if I apply a pressure difference, okay, delta p, okay, across the ends of a pipe, okay, of length L, what is the variation along the x direction? What is the pressure variation along the x direction? That we can infer from this equation by just taking one derivative of the equation with respect to x. Okay. So, I will take the derivative with respect to x of the entire equation. Okay. And on the left side, since time and x are independent coordinates, I can interchange the order of differentiation. Okay. I can interchange the order of differentiation because time and x are independent coordinates. Okay. Partial by partial t of partial Vx by partial x. On the right side, similarly, I can interchange the order of differentiation because time r and x are independent coordinates. Okay. R and x are orthogonal, r is along the radius, x is along the axis. Since these are orthogonal coordinates, I can interchange the order of differentiation because I am taking partial derivatives. When I take the derivative with respect to one quantity, one spatial variable, I keep the other one a constant. And these are two independent coordinates. So, I can write this as nu by r d by dr of r d by dr of partial Vx by partial x. Okay. And incompressible flow pressure is a constant, incompressible flow density is a constant. So, therefore, there is no derivative of the density with respect to x. So, I will get minus 1 by rho d square p by dx square. Okay. And recall that we had derived this condition that dVx by dx is equal to 0. Okay. The derivative of the velocity with respect to x is 0. That means that this term is 0, this term is 0, and therefore, d square p by dx square, this has to be equal to 0. Okay. D square p by dx square, the derivative of p with respect to x square, that has to be 0. Okay. So, first things first, because there is no variation of p with respect to r, okay, I can as well write this as a total derivative. Okay. Okay. Because p is varying only with x, okay, p is varying only with x. I told you that there is no variation of p with respect to r. That means that I can write this one as a total derivative, okay, because it depends only upon x, it does not depend upon r. Okay. For the laminar flow in a pipe. Okay. And so, this becomes the total derivative, okay, d square p by dx square, that has to be equal to 0, which means that dp by dx has to be a constant. Okay. dp by dx is a constant, that means that the slope of the pressure with respect to the x coordinate. Okay. If I plot pressure as a function of the x coordinate, that has to be a linear function. Okay. It has to linearly decrease from one side to the other. Therefore, dp by dx is equal to a constant. For a pipe flow, incompressible pipe flow, unidirectional, the pressure has to vary linearly between the inlet and the outlet. The pressure at the inlet is higher than the pressure at the outlet in order to drive the flow. Okay. The pressure at the inlet is higher than the pressure at the outlet in order to drive the flow. Okay. Therefore, dp by dx is a negative constant. Okay. dp by dx is a negative constant. In the discussion, we will use minus dp by dx as a positive quantity. Okay. We will use this minus of dp by dx as a positive quantity. So, I have discussed derived the conservation equation for you. Next lecture we will solve this in order to get the correlation. First the shear stress, the wall shear stress, the average velocity, the maximum velocity, and from that the friction factor correlation for the laminar flow in a pipe. I will continue this discussion in the next lecture. I will see you then.